here we have two tanks, one with 12,000 gallons of water and the other one with 10,000 gallons of water. We're going to assume that those are pure water. And we have an external source with 5 pounds of sugar per gallon, and with a constant flow in and out of 100 gallons per day, we end up getting 500 pounds of sugar per day. And we see here with our model that it's going to continue flowing through until we reach equilibrium of sugar amounting in 5 pounds of sugar per gallon. So that's already like a little trick for the end, but we're going to continue on and I'm going to set it up in and outs, right? And that the flow at which x is changing over time is the input minus the output. We get these two for x, dx and dy, dt, right? And we set them equal to 0 because the slope will not be changing. We solve for them. We end up getting our equilibrium points, sorry. And we see that as time goes on, x and y will eventually get to a point where they're no longer changing how much pounds of sugar they have, which will be the 5 pounds of sugar per gallon, as we see here. We solve all of that by just making a model with what we have. Next, we have a second order differential equation. Sorry for the transition. And we're going to use Laplace transform to do so. Okay, so we have the second order, so we're gonna do each component, and then we're gonna be able to isolate this Laplace of s to then solve for y of t by first putting in a partial fraction calculator and then doing the inverse Laplace to derive what y of t is, and we plug this into Desmos and get oscillations, amplitude, period, our frequency. So here we go with our y of t equaling that. And we can see that this is everything that the problem asks for. As we find that over the long run behavior, it's going to continue oscillations from around 3/2 with an amplitude of plus or minus 1/2. And it takes only 4.44 seconds to do so. And it's really simple stuff.